Welcome everyone. Today we will shift our discussion towards vector calculus after we are done with vector algebra. Another word for calculus is analysis. Analysis is the fancier nomenclature for calculus. Calculus is more historic as a word, more intuitive. Right, when calculus first emerged, it wasn't that rigorous discipline. It was more intuitive, and then slowly, as the centuries passed, mathematicians started putting it on a more rigorous backbone. Started giving it a more rigorous backbone. What is it about, essentially, calculus? It's about, as you know, differentiation and integration. And it's about limits. So the idea with differentiation is a difference, essentially. So you take a difference and you take the limit of that difference as delta x goes to 0. Integration is just the sum. So you take an interval and then you sum along that interval, but then the number of points you sample goes to infinity, right? So as you add in more points that you are summing, the sum goes to infinity, so you need to kind of bring back the sum to some finite limit. So you have to multiply the sum by some number, and this number is typically delta x, right? So that you can get a limit. So I mean, I'm gonna assume that you know calculus. I'm not gonna do calculus from scratch here, but the idea is that one-dimensional calculus on the real line, the entry point for it is either through differentiation or through integration. Now, for electromagnetic theory, we want to develop the theory of vector calculus, which is a theory of calculus in 3D space. And from that point of view, from the point of view of 3D space, it turns out it is easier to enter into calculus from the integration point of view. It's much easier to start with integration and then use integration to develop differentiation. Right? We will find out that it's much more easier to understand that there are many ways to integrate in 3D space. You can integrate along a line, a surface, a volume, but it's harder to understand that there are also many ways, multiple ways to differentiate in 3D space, three-dimensional space. And entering calculus through integration in 3D space is going to be our springboard into hopefully intuitively understanding why do we have different ways of differentiation in 3D space. So let's review a bit the gist of calculus in one-dimensional space. In one dimension, essentially calculus on the real line. So this is R, the real line, right? What is the idea of calculus on the real line? And let's take the point of view that I like to take when introducing this subject, which is that integration is the fundamental thing that you do, the fundamental operation that you do, right? So let's take that point of view, that integration is the fundamental thing that you do, right? So and from that you get differentiation. So integration on the real line is essentially you have a function on the real line, f of x, and essentially at every point on the real line there's a value for that function. So this is x1, x2, x3, x4. I guess let me start from x0, right? And then x5 dot until you get xn minus 1 and then xn. right? So you take a sample of points on the real line. You start from a certain point and you end a certain point. So there's an operation you can define, which is essentially summing the function at those points. So at each point, this function has a value, fx0, fx1, fx2, fx4, and so on and so forth. So the idea is that you define an operation where you sum over you sum the value of the function at those points, right? And the idea is that there's not a finite amount of points. What you do is you take an infinite amount of points. So you start with 5 points, and then you go through a process where you keep increasing the number of points. Then you go from x0 to xn, you start with 5 points, let's say. Then you go to 6 points, and then you go to 7 points, 8 points, 10 points, a million points. So it's a process that you go to, and that's where the word analysis comes from. It's a process, infinite process, that somehow still reaches a limit, reaches a definite value. So does this sum reach a definite value as I increase the number of, so this goes from 0 to n. As n goes to infinity, n is going to infinity, does this sum reach a definite value? No. Clearly, it reaches infinity. So what you need to do is you need to multiply this by some term that is going to reduce the sum. So this term is called the measure. So you might multiply this by xi plus 1 minus xi. This, or some people call this delta x, the difference between a future point and a past point, right? So this sort of thing is called the measure on the integration. And what it does is that although you're summing an infinite number of points, so the sum needs to go to infinity, you're applying a measure. You're scaling every item in the sum by a value, by a number that's approaching 0. So you're summing an infinite number of numbers, infinite, that's a funny thing to say, infinite number of numbers, where each number is approaching 0. Somehow this thing reaches a limit, right? So as limit as n goes to infinity, this reaches a definite number, which is the area under the curve of the function. If you draw the function like that, it turns out to be the area under the curve, right? So this is what analysis is all about. You have some process that is repeatable, that is infinite. You can keep doing it an infinite amount of you can keep making it finer and finer and finer, but then it reaches a certain definite answer. You get a certain different computation at the end. This we designate as this symbol. This is an elongated S for sum. This is integration, and you're integrating from x0 to x, let's call it x xn, f of x dx. This essentially symbolizes what's happening here. Okay, this is analysis. This is integration. How does this lead to differentiation? Well, let's say, how can this understanding of integration directly lead to differentiation? Well, let's say you're integrating on the real line. So this is the real line again. You're going from x0 to xe, and then you're integrating on the real line. There is some function on the real line. You know, this is xi, and then you have fxi. So you're summing this function from x0 to xe. So you know that one basic property of the integration is that x0 to xe of x dx is just the integral from x0 to xi f of x dx plus the integral of xi to xe f of x dx. You can separate the regions of the intervals of integrations into sub-intervals. This is very intuitive because the integral is just a sum. So you're summing across this interval. You might as well imagine that the sum across this whole interval is equal to the sum across this sub-interval plus the sum across this sub-interval. So nothing fancy here. This is really a very intuitive statement to make. But the more interesting thing about the property of integration is that it's linear. So if you integrate alpha fx plus beta gx dx from a to b, this equals alpha a to b fx dx plus beta g to x a to b gx dx. And this linearity is also clearly seen from understanding the integral is just an infinite sum. You know, if you sum something that has components, that's equivalent to summing the components separately, right? Right, so this is the basic property of integration. Where does differentiation come from? Differentiation comes from examining the exterior of the region of integration. Meaning, is there a way this integral, so again I will draw the real line again, and emphasizing the real line, one dimension real line this way, rather than doing a graph plot of a function, because this is going to be the springboard for going into 3 dimensions, right? So again, I'm integrating from x0 to xe. I want to express this integral. I'm integrating some function x. This is f of x. This is point x, let's say. I want to express this integral of f of x dx from x0 to xe right? So there is 2 ways to get this integral. One way is to just go and sum, take an infinite amount of points between x0 and xe, multiply those points by the measure, which is delta x, take the sum, take its limit of this infinite sum, and that's your integral. However, it will be interesting to figure out, hey, is there a way to express this integral in terms of the boundary? What is the boundary in this case? The boundary in this case is this point and this point, right? Is there a way to, is there a fancy way where we can write this integral directly from the boundary instead of looking into the region and summing all the points? Is there a way to write this integral with respect to the boundary? Is there some other function, let's call it big f of x, that exists such that we can write this integral as f xe minus f x0? So you now write this integral in terms of its boundary, right? And furthermore, we want to be able to derive or get f capital X from fx through some kind of operator. There should be some kind of operator that should give us f small x from fx, or vice versa, let's say. Let's examine if such an operator exists, right? So let me see here. Let me go here and say, hey, let me assume there is some operator that if this operator acts on f of x capital, it gives me f of x small. So there is some operator. This operator, if it acts on f capital X, excuse me, it gives me f small x. I'm assuming there is some operator. I don't know what this operator is. Well, it turns out this operator is exactly what differentiation is. Right? Why? Well, assume this interval here collapses to 0. Assume we take a really small interval where xo and xe are really close to each other. So if xo and xe are really close to each other, the function the function, whether it's capital F or small f, is going to be constant. So fx is approximately going to be constant. F capital X is approximately going to be constant over the small interval. If we have a constant function, so this is small fx, right? If we had a constant function, we can always take it out of the integral. So we end up with O fx, right? Integral of dx from xo to xe. This is e minus xo, right? This is delta x, right? Equals fx end minus fx0. So this operator acting on fx for a small interval is really fxe minus fx0 over delta x, xe minus xo. Right? This is as xe approaches xo. This is differentiation. Exactly. This is differentiation. Right? So by starting with this requirement or this hope that we can write the integral as something to do with the boundary of the interval, we arrived at the fundamental theorem of calculus. We've shown that if I integrate f small x, which is something that we get from applying an operator on fx, capital, and this operator is the differentiation operator, which I write as d dx. Instead of O, I wrote it O here because I didn't want to give you the answer. You know, I didn't want to cheat. I wanted to assume a general operator, which turns out to be exactly the differentiation operator, right? Dx, this equals fxe minus fxo. This is the fundamental theorem of calculus. Right? And this is how we can define differentiation if we start calculus from integration. So if we define and understand integration first, we can easily define differentiation in terms of this what's called the exterior property. This is in a very general terms. Sometimes the subject is called, this way of looking at things is called the exterior derivative, especially if you kind of try to generalize it towards higher dimensions. The key thing is that this is, in my opinion, the easiest way for us to understand calculus in higher dimensions. In one dimension, it's easy to start with differentiation and then go to integration and then relate the two. But I think in higher dimensions, it's easier to start with integration. And then use integration, use something similar to this, where we define the integration by some function of the boundary to define, essentially establish higher dimensional forms of the fundamental theorem of calculus, which allows us to define differentiation at higher dimensions. So essentially, we're trying to approach differentiation in higher dimensions by defining integration in higher dimensions up to three, using that to define the different kinds of differentiation in higher dimensions. That's the easiest approach. This approach is also called, theoretical approach is also called Stokes theorem. Sometimes you'll hear Stokes theorem. I mean, there are all the different kinds of theorems, that Green's theorems, I believe, or something like that, that are all similar. So special cases in 2 dimensions and 3 dimensions, but they all generalize to the same thing. It's all the fundamental theorem of calculus. Right? So yeah, so this is such as just an introduction to what we want to try to do. But if we were sticking with 1 dimension, that's going to be regular calculus that you studied. We want to now move to 3 dimensions, and we want to start with integration. Right, so we want to start with integration. Integration is just summation, right? And it's very easy to define in 3 dimensions, right? It's very easy to see that there are different kinds of integration, right? So I have my space, I have my three-dimensional space. I have a function on this space. Let's say I'm using fx, y, z. I'm using the Cartesian coordinate system to label the space, right? So there are three kinds of integration. I could integrate over a line. I could start at some point, x 0, y 0. Let me call it p0. I could start at some point p0, and I end at some point pe, and then I can walk along a curve, a line, a curve. And then I can, as I'm walking, I can take points and I can sum the function, right, along this line. Right? So this sort of thing, where I'm summing the function along this line, and then of course I'm not gonna have a finite sum, I'm gonna have an infinite amount of points. I'm gonna take a limit as the number of points on the line goes to infinity. And I'm gonna apply a measure of delta L so that I can get a finite limit. Although I'm summing an infinite amount of numbers, I want to get a finite limit. So this sort of thing is called the line integral. So this is one way of integrating, right? And this requires us to define a line element. We're integrating across a line element. A line element will have a direction. So it's going to be a vector. Okay. So this is one common way of integration. Another way we can integrate, notice on the real line, our options were limited. We can only exist on the real line. There is no degrees of freedom. We can only sum on the real line. While in 3D space, we have three options. So this is option number 1. Option number 2 is I can take some surface. This is 3D space. I can take some surface on 3D space. This is, imagine this is a rug or, I don't know, a membrane or whatever, a surface. And then I can take small squares on the surface. I'm not going to draw them all, draw some of them. And then I can take the center point on each square, and then I can sum fx, let's say I, yi, zi. I can take the sum of all those values of the function at those points, but then I take the sum, infinite sum, but then I need to apply a measure so that this sum goes to some finite value. The measure is going to be delta S. Delta S is the area of one of those small squares. So this small square on the surface is called an area differential element. So this is an area differential element. And we can use this element to divide a surface, any surface, to small elements such as those, so that we can do this sort of integration. This sort of integration is called the surface integral. And this is the second kind of way we can integrate in vector calculus. The third, of course, is volume integral. So I take a certain volume. Let's say I take a cylinder. I need to divide this cylinder into small cubes. I'm drawing them as circles, but they are, imagine they are cubes, right? So those are dV elements. Those are called volume differential elements. And using those and taking the sum over a volume and taking the limit by applying dV as the measure, I get what's called a volume integral. Right? So the key to define integration is figuring out how to mathematically represent those small elements, what's called integration elements. For one-dimensional calculus, it's easy. It's just delta x dx. But for three-dimensional space, it's a little bit more subtle, because there are three kinds of them. There is the line elements, or what's called length elements, and then there is surface elements, and then there is volume elements. So let's go define those integration elements intuitively next. element. So let's start with what's called the length differential element, right? And this is a vector, right? Because we are in space, we are integrating. Let me adjust this. So we're integrating from one point to the other across a line, across a curve. So if I zoom in, I'm integrating across a directed segment, right? So at each point in the curve, I'm facing a certain direction, right? So this directed segment I'm integrating across is a vector, right? It's called dl. D signifying that it's a small directed segment, right? So we integrate across a linear path, and that linear path has a direction, and we specify this direction by signifying dl to be a vector. Dl doesn't have to be a vector. It could have a scalar version of dl, where I don't care about the direction of the segment, for example. That's possible to do that. But the more general way of describing the differential element is as a vector, right? Because you're always, when you're integrating across a line, across a segment, across a curve, at every point in the curve, you're pointing in a certain direction as you're moving. You're moving in that direction. You're moving across that directed segment. So that dl mathematically can be expressed. To express it mathematically, we need to know what the coordinate system is. So let's say you're at point P and you walk on that curve and you're moving in this direction, dl, right? This is a vector at that point. This represents a directed segment at this point. This represents, hey, at this point, I'm walking on the curve, I'm walking in that direction, a distance dl vector magnitude, right? This is kind of like the delta x from calculus, right? So this is a vector, and you need you can express as a vector at every point, right, using the coordinate basis and the coordinate system. So same way we can express dl based on our coordinate basis and system, meaning that there are multiple ways of expressing dl. We could either express it in Cartesian. In Cartesian we would express it as dx, a small change in the x coordinate, times x hat plus dy y hat plus dz z hat. Makes sense, right? So this is in Cartesian. This makes sense, like a directed dl displacement is the sum of three displacements. So this displacement is the sum. Let me draw it in a clearer way here. So this dl here, I'm expanding it, although it's small, is the sum of three displacements. It's the sum of a displacement in the x direction, dx x hat, plus a displacement in the y direction, dy y hat, plus a displacement in the z direction, dz z hat. Let me draw dl such that it points from the start to the end. Right, this is dl. So you can always write any displacement as the sum of displacements across the x, y, and z axis. Right? I mean, that's intuitive. Right? This is from vector algebra. You know, this plus this plus this gives me, right? They're all connected, head to tail, head to tail to head, tail to head, tail to head. Right? Those three vectors add up to give me the resultant dl vector. Okay, so this is in Cartesian. In cylindrical dr, we move along the r axis, the r coordinate, r hat. However, now when we move across d phi is an angle. An angle does not have length, is not length, right? We need to convert this angle to length, right? So when we are starting at a point and then we move across the r direction. So this is r hat dr, and then we increase phi. Phi is increased in this way. Let's say phi is not a length, so this is d phi. D phi by itself is not a length. D phi by itself is not a length. It's an angle. What's the length here? Let's call it let's call the length here h. Right? H is gonna be, what is d phi defined as? The angle in radians is just this length h divided by the radius of the circle, right? The radius of the circle that this arc takes. If this arc goes to 2 pi, we do one full circle, right? So what's the radius? The radius is just r, right? How far we are from the origin. So d phi is really h over r. So this small displacement h is just r d phi. So this is how you turn the d phi infinitesimal, which is dimensionless, into a length by multiplying it by r. R d phi gives me the length element, phi hat, and then finally dz z hat. So this is cylindrical. Right? Now expressing this in spherical is also easy. Right? So I have dr r capital hat plus the theta direction, in the theta direction. So I have here, I go in the r direction, right? So this is dr. So this is the point r theta phi, and then I displace by dr r hat, and then I displace phi theta. Theta goes in this direction, and again this is an angle, so this displacement is just going to be r d theta, similar to what we did here, right? The displacement is going to depend on the radius of the circle you're moving along, right? And then finally, the final part is going to be the displacement along the cylindrical coordinate phi, the angle phi. Again, this is an angle, so this has to be multiplied by something to get a distance, right? So what is the radius in this case? The radius, so this has to be the small radius r, right? This should be the projection of r capital into the xy plane. That projection is going to be, we said, is r sine theta. So this is the radius of the circle that phi traverses, right? So that's going to be that would act instead of the radius. It's going to be r sine theta, and then it's going to be multiplied by d phi. So it's going to be r sine theta d phi. That's the length element in the phi hat direction. So this is how we write the length element dl, decompose it into the basis vectors for spherical coordinates. And this will be useful when we define integration. We can always integrate across vector elements like those, and then we decompose it into the bases, and then we divide. Because the integration is linear, we can turn like integral into 3 integrals. We can integrate across each component, essentially. Okay. Now, from the length elements, we can derive what's called area differential elements. Right? So starting at a point, and again, I can use Cartesian system. I can extend in the x direction, and then I can extend in the y direction, and then I have an area element. Or starting from this same point, and I can extend in the y direction, z direction, I have this area element. Or, so this area element is in the xy plane. This area element is in the YZ plane. I could have an element if so here I extended in x and y, I extended it in y and z. I could extend an x and z, so I'll get this element. So this is in the xz plane. So there are three different surfaces pointing. So this surface, the face of this surface, its face points towards in the same direction as the z-axis. The face of this surface points in the same direction as the x-axis. The face of this surface points in the same direction as the y-axis. Right? So there are different orientations. There are different, we can compose different differential area elements. So we can designate those as the dsx. Right? So dsx, this is where the face of the surface is pointing in the x-axis to the x-axis. So we write this as dy dz. This would be the differential element. dsy is going to be, because this is here, this is dy and this is dz. Right? dsy, where the face of the area is pointing towards the y-axis, same direction as the y-axis, this is differential area dx dz. Right? To do two small displacements, give me an area, right? dsz is going to be dx dy. This is in the Cartesian system. So those are Cartesian surface elements. However, we can define also cylindrical surface elements, dsr, ds ds, right? So essentially dsr means the surface, so starting at a point, the surface area such that the small r axis, so the surface area, so if this is the point, it's the surface area, let me draw it like this, such that the r axis, our small axis, is perpendicular to that surface area. So what are the sides of those surface area? The sides of those surface area is going to be this side, which is rd phi, and this side, which is dz. So this is going to be r d phi dz. Or I could have taken it from here, from dl. I could have said, hey, perpendicular to dr, what's perpendicular to dr? The other two vectors, right? Basis vectors. So so this and this. So I just take this multiplied by this, right? Instead of doing this drawing. And then ds phi, the surface area that has its face facing in the same direction of phi. I can take it from here as this times this. So it's going to be dr dz. So this is going to be dr dz. And finally dsz, I take those two that are perpendicular to dz. I'll get r d phi r d phi dr. So those are the area differential elements in cylindrical coordinates. And the same way we can write the surface area elements in spherical coordinates. The surface element that is oriented in the same direction as the r coordinate, capital R coordinate. The surface element that is oriented in the same direction of the theta coordinate at the point. The surface element that is oriented in the same direction as the phi element in the point. And remember, in 3D space, there is always going to be three orientations of any small surface. So DSR, I'm going to go to the definition of DL. So perpendicular to r hat, so this is going to be this times this. So it's going to be r squared sine theta d theta d phi. So this is going to be r squared sine theta d theta d phi. Simple. All you need to know is the linear differential element, length differential element, which you can reason about, and then you can derive the surface elements from it. Right? ds theta, I have now to take this dr times this. So it's going to be r sine theta dr d phi. So it's going to be r, come on, don't do this, So this is going to be R sine theta dr d phi, and then ds phi is going to be, let me go here again. So I'm going to take this times this. It's going to be r dr d theta. So it's going to be r dr d theta. Finally, the volume element, you guessed it, you just multiply the three linear elements together. I don't know why the screen is acting this way, right? So the volume differential element, dV, is simply dx, dy, dz in Cartesian. In spherical, it's going to be r d phi, dr, dz. This is in cylindrical. Just multiplied all the length elements together. And then for spherical, is going to be r capital sine theta. I multiply all the length elements, so it's going to be there's going to be dr in there, right? There's going to be d theta. There's going to be d phi, and then I have extra. I have r, and I have r sine theta. There's going to be r squared sine theta. Okay, so I multiply everything together to get the volume element. One last point I want to make. Notice that the surface element always comes in three flavors. So it seems that any small surface can have three different orientations. But what if I have a general surface that has any orientation, any random orientation? See here, I'm sticking to surfaces that are either oriented towards the r-axis or theta axis or phi axis, or oriented towards the x-axis or y-axis or z-axis. But areas don't have to be oriented to either the x-axis, you know, y-axis or z-axis. You know, they could have, I'm drawing arrows to represent the orientation of the area. They could have some random orientation, you know, they could have this orientation, right? Because surfaces can have random orientations, surfaces act like vectors. I can, although this is not exactly very rigorous, you could, I mean, surfaces are not really, if you really go deep into it, they are not really vectors, if I want to be pedantic about it. But at this stage of development, and probably not until much later, I mean, even, they are, for all practical purposes, vectors. So I think of them as vectors at this stage when I think of those sorts of problems, right? But someone might tell you, hey, Ihab told you those are vectors, but those are not vectors. Well, for all intents and purposes, they can be considered vectors in this area of study. Okay, so because they have orientation, and you can consider the orientation of the surface area to be vector-like, and I can represent any random surface area as the sum. I can, if I take this in 3D space, I can project this here on the XY axis plane. I can project this here, and I can project this there, right? So I can take this as three projections, one on the XY plane, one on the XZ plane, two here, and one on the XY plane. And I can write this small oriented surface as a sum of those three surfaces. So in that sense, areas can be vectors. And the way we write them is that if I write dsx as a vector, I write dy dz, and then I put in the unit vector to represent the direction of the orientation. In this case, this is oriented towards the x-axis, so I write ax hat. Right? So this is the unit vector in the x direction. In this case, this is x hat. Right? Plus minus. In my notes, I say AX hat. I think I was using different. So X hat is the same as AX. So if you see AX like this is the same as X hat. Okay. Perhaps I need to correct that in the notes. I don't know why I went with that notation, but dsy is plus minus dx dz y hat. The reason for the plus minus is there's an ambiguity. Is that if I have a surface oriented towards x hat, it's ambiguous whether the orientation is in this direction or that direction. Right? You have a surface. Which is the front of the surface or the back of the surface? Is there a way to tell for sure? Right? It's a matter of perspective. What's front or back? Right? The orientation of the surface is optional. It either could be, you know, this side could be the front or the back side could be the front. Right? That's why I have plus minus. And then dsz is going to be plus minus dx dy z hat. Same thing for cylindrical and spherical. I won't write it down. And then the idea of writing this as a vector is that those area elements, oriented area elements as a vector, is that I can write any general area. If I have any general small area segment that has a random orientation in the direction of a vector A, let's say it's oriented in the direction of a vector A, general oriented surface, let's say it's oriented this way, can be represented as a vector A, where a vector dA, so this is a small area. Remember, if it's a big area, we cannot talk about the global orientation, because a big area can be like something like this, can be wavy, you know, can have waves in it and bulges and whatnot. So we cannot talk about orientation. It's pointing everywhere. It's like we can only talk about orientation of area if we talk about a small area, really small, tiny area. So a small, tiny area, infinitesimal area, we can talk about orientation. It's pointing towards somewhere. So using this kind of mathematics, we can represent this area by a vector, small vector, dA, where dA vector is just plus minus dA. dA is a scalar that represents the actual value of the area. So this is the actual area, dA. It's a scalar. And then n is the vector normal to the orientation of the area. So n is this vector, this unity vector that's pointing in the orientation of the area. So this is the way of representing any general area. Any general oriented small area disk can be represented as a magnitude and a direction. And this is how you represent it as a vector. This vector encodes the magnitude of this vector, encodes the area of this really tiny segment, and the direction encodes the orientation of this tiny segment. It is convention for the sign to always be selected such that the orientation is pointing outside an enclosed area. So if I have an area, let's say I have an area that's enclosed, I have a potato that's, you know, a surface of a potato, let's say, and then I have a small segment. It's conventional for the small segment to select the orientation pointing outwards, right? So this is n hat. It's conventional to select it such that it points outwards from the enclosed area, which is the interior of the potato. It's just a convention. When you solve problems, this is the convention to use. If it's not a closed surface, if it's like, let's say, a rug, so this is a rug, and I have a small area segment, then it's conventional to select the orientation, right, such that if we are traversing, let's say if we are doing something where we are traversing the boundary, right, So it's conventional to select the orientation such that when we the orientation matches traversing the boundary counterclockwise. You're using the right-hand rule. So if we are doing something where we are integrating over a boundary and we're traversing the boundary counterclockwise, then it's conventional to select the area such that it's pointing upwards like that. If we're going clockwise, it's conventional to make select the direction to be pointing downwards. Using this is the right-hand rule. So this might be confusing right now, but this will be clearer when we do actual integration problems. Okay, so this is enough. This is one of those things that are going to become much clearer once we dive deep into doing actual integration. And I believe we can do that next time. So integration part 2 is going to be next time. Thank you, guys.